Hi, my name is Zhengqi Zhu, and I'm here for presenting my CS224n final project, Reproduce Simple QANet on Squad 2.0. The problem we're facing is to build a question-answering deep learning model on Stanford question-answering dataset. In this dataset, the input will be a paragraph of context and a question, and our model could find the answer in the given paragraph as the output, not generating the answer. My project is to successfully implement QANet with PyTorch and build a question answering system using the model. For building the model, I followed the QANet paper called QANet Combining Local Convolution with Global Self-Attention for Reading Comprehension. By the time this paper was published, most of the end-to-end machine reading and question answering models are primarily based on two key ingredients: recurrent neural networks, aka RNNs, and attention mechanisms. However, despite the success of accuracy of these models, they are comparatively slow to train and inference due to their recurrent nature. This weakness leads to a high turnaround time for experimentation and limits researchers from rapid iteration. Also, it prevents the model from being used for large datasets and being deployed in real-time machine comprehension system applications. The higher level architecture contains 5 layers, as shown in the figure 2. The high-level structure of this model is similar to most existing models that contain 5 major components: an embedding layer, an embedding encoder layer, and context query attention layer, a model encoder layer, and an output layer. The major difference between QANet model and most existing reading comprehension models is that for both embedding and the modeling encoders, only convolutional and self-attention mechanisms are used, discarding RNNs. This results the implemented model reaches a better performance compared to the given baseline model with fewer number of epochs trained. An extension of my QANet model is that I applied a mask on the self-attention layer to remove the unnecessary attentions and let attention focuses on some of the keywords. To evaluate the performance of the model, we have EM and F1 scores. EM score is exact match score that is a binary measure of whether the output matches the truth answer exactly. The F1 score is a harmonic mean of precision and recall. I used Google Colab Nevada Tesla P100 GPU with 16 gigabytes memory to train my model, but due to the limitation of the memory, I have to limit the model size from the original paper. The results seemed pretty good since the baseline model could get EM score of 56 and F1 score of 59.57. And QANet model reaches EM score of 63.86 and F1 score of 67.68 on the development side, with half of the epoch number trained. Also, on a test set, QANet model could get 62.42 EM score and 65.75 F1 score. There are some improvements that I can still do in the future. In the paper, the researchers used a data argument technique that can translate the input dataset to French and then translate back. In this way, they will have twice large datasets for training. But due to the limitation of time and I was doing this project individually, I'm not able to do all of it. In conclusion, the project successfully reproduced a simple QANet and the performance has achieved the target that is higher than the baseline model. With applying the mask on the self-attention layer, I got a better performance than the model without the mask self-attention layer. Thanks for watching.